And there is a saying that in maths, everything is either solved or unsolved or linear algebra. So once you solve anything in maths, it becomes linear algebra. So we have to use linear algebra, like no matter what area of maths you are doing, we have to use linear algebra somewhere or other.
Wow, that's a powerful
Okay.
statement.
There is
Jeez.
nothing like we can comfortably do in maths, which is like something absolutely not like linear algebra.
Okay.
Okay.
Wow.
So let's start with very basic. So we want to study linear stuff. So line, we know equation of line looks something like this, y equals mx plus c.
Yes.
So that means if we want to have a linear function, so this should be called a linear function, right? F of x equals mx plus c. So where a and c are some constants, you plug in a x and you get the f of x values. Now the thing is, this is good, but mathematicians use a slightly different definition of linear. The definition looks something like this: f of x plus y, or rather, I will put different letters. F of u plus v should be equals f of u plus f of v. So if you put two inputs, you should be able to add the outputs to get the combined output. That's the other way of thinking of linear. And another consequence of that is f of n times u, where n is a multiple. That should be n times f of. Make sense?
Yes.
Now with this definition, you will see that this plus c, which if you have a c something non-zero, then this would be 1. So what we do is we call these functions affine functions. And then my linear functions are basically f of x was some m times x. So this is a linear function in one input. Now, if I have two inputs, something like f of x comma y will be some m times x plus n times y. That's it. Okay.
Got it.
And then if you want something like two inputs and two outputs, so it will be something like f of x comma y was first output will be like f of mx plus ny. The next output can be something like, let's say, ax plus by. Okay.
Okay.
So all this is linear. Now you can see there are two things arising here. Uh, there are inputs are not really just numbers now. There are a bunch of numbers. So we want to store that data like x and y. There are two inputs. I want to store x and y and give it a single name somewhere. Or if you are thinking in terms of code, I want a structure that will hold both an x and y as its members. So create a class or something in Python or some other language that will hold the x and y fields. So that automatically arises out of the vectors. So x and y combined will be called a vector.
So X
Okay?
is not a X is a vector
X
itself.
is a coordinate of the vector. Y is one of the second. X is first coordinate. Y is the second coordinate. And
Yeah.
x and y combined is the vector.
Okay.
Okay. So the function takes two things as input. That two things combined, I want to like write down a single thing that is coming as an input. So I will write down as u. So let's say it's u is x comma y. There I
Got,
can write f of u.
got it.
Something for it, right? And the second thing is, so the output is linear. So what I only want to store is the coefficients. So m, n, a, b, right? Now that coordinates I can store is the matrix. So let's say that matrix is A. So I write f of u equals A times.
Okay.
Okay. So this statement means the same thing as this previous statement, except the notation is much more compact. So like when you are writing a lot of stuff, it helps to have a compact notation.
Got it.
And we achieved that by first introducing a vector u and then introducing a matrix A. Okay.
Got it.
So this is just to motivate you that vectors and matrices automatically arise if you are trying to have more than one information going input and output.
Got it.
Okay.
This is
So
maybe this is like outside of the scope of this, but I think
yeah,
it covers from the beginning this question that I'm going to ask from the beginning.
yeah,
Everything we're seeing is linear though. So Jay,
yes.
what if we immediately just put an x, like why are we not even considering x squared? Like that seems
Yeah, that's a very good question. And I will give you examples of how even people who want to study x square and more general like polynomials and all, that also can be done using linear algebra. There
oh,
are ways to study polynomials using linear algebra. We'll give examples.
okay. Okay.
Okay. So polynomials are not too difficult for linear algebra. Even sines and cosines also fall under linear algebra.
Okay.
Okay. So you can like there are as an you get new areas of maths, they get absorbed into linear algebra.
There's ways to represent it with linear.
There are ways to represent them using linear algebra.
Got it.
Okay. So that's the basic introduction of why we need vectors and matrices.
Cool.
Okay. So now let's move on to vectors. So vectors, like we discussed, so like our function had two inputs. So we will say it's a vector of two dimensions.
Okay.
Okay.
X, Y, yes.
So yeah, I'm not telling you what the word dimension means for now. We'll define
Right.
dimension later on.
Okay.
But like it just means it has two coordinates. Similarly, you can have three-dimensional vectors and so on. And we can also have polynomials as vectors. So I'll show you one. So let's say P of X equals set of all polynomials as vectors. Okay. Now let's suppose you give me a polynomial. Just give me something.
X squared minus 2x plus 1.
Okay. So I will write it in increasing order. So I'll write the constant term first and in the opposite order. Basically. So 1 minus 2x plus x squared, right?
Yeah.
Okay. Now we know that any polynomial will have this 1x, x squared, and so on. So all I need to store is the coefficients. Make sense? So I will only store the data 1, minus 2, and 1.
What is P here? P is
P is the polynomial which I'm storing. You can use a different letter or
okay.
something else, P hat or something.
Okay. Okay. Got it.
Or let's say P star.
Okay.
But what I'm saying is that this storing this polynomial data is as good as storing this vector.
Got it.
And then if you want to add two polynomials, you add coefficient was right. You add the x square terms, you add the x terms, and so on. This will the same thing will happen with the vector also. You will add the first coordinate, second coordinate, third coordinate.
We've made it into one dimension then. We've
Yes.
made this polynomial.
Yes, yes.
Okay.
Just by representing the data in terms of coefficients, we have absorbed the polynomials as vectors.
And if there's a missing, like if it was one,
yeah, you put 0.
You'd put 0.
If there is a missing term, you put 0.
Yeah.
Okay. So, for example, I can have.
You did say, is it typically done in increasing order of the polynomial, like constant?
It is not necessary, but it's easy for me now because let's say I have two polynomials, and one of them ends at x square. The second one goes up to say x power 10 or something. So if I do it this way, I can append some zeros at the end.
Got it.
Which is easier than appending 0 at the beginning.
Got it.
So I have this, there right P star equals 1, and then 0, 0, minus 1. Right.
Got it.
So we have convinced ourselves that all these things can be done with vectors. Similarly, functions can also be done with vectors, like sines and cosines and stuff, but I won't give those examples right now. We'll come to that later.
Okay.
But the idea is all functions are vectors. Now, one thing that we have noticed with all these vectors is the vectors have coordinates. Like two-dimensional vectors would have two coordinates, which I'm calling the first and second coordinate. You can call it x and y coordinates sometimes, depending on the problem statement and which area of maths you are doing. You can have x, y, z coordinates when you are doing vectors in physics, maybe.
This one, when you're saying coordinates, are you talking about directly on like a plane, like XY plane and XYZ?
You can think of the geometrical XY plane also. You can think of algebraically the coordinate, meaning the individual components also.
Okay.
Both are same thing.
Okay, got it.
Okay. So we have the vectors as coordinates, and then you can do vector addition is coordinate wise. This makes sense?
So just
you add the first coordinate, you add the second coordinate, and so on.
Yeah.
Okay. And then you have also something called scalar multiplication, which is like you can do C times a vector, which will be CV1.
Yes.
And then CV2 up to CVN. So you multiply all the coordinates by the same constant.
Yes.
And this constant C are called scalars because they are not vectors. So we can multiply the scalar across all the components easily. Now, these are the two basic things we should be able to do about any vector. We should be able to add them, and we should be able to multiply with a scalar.
Yes.
Okay. Now, anything where you can do these two things, we can do addition and scalar multiplication under certain rules and all. For example, u plus v should be v plus u, and so on. That's called a vector.
But we can, sorry, this is jumping maybe because I
Yes.
think I know the answer. We cannot multiply a vector and a vector where it's just A times A1, B1, A2, B2. We can't multiply.
In general, no. No,
In
we
general.
cannot do that.
The special way to multiply those.
Yeah, there are special ways to multiply. I'll come to multiplication.
So scalar, though, we could just multiply this
Scalar, we can easily multiply.
through there. Okay, got it.
Okay. So, and then there are some special vectors which are called coordinate vectors. So I'll write them for 3D. I think you might have seen these kind of things in physics a lot. So I'll write E1 will be 1, 0, 0. E2 will be 0, 1, 0. And E3 will be 0, 0, 1. So these are the three vectors. And then any other vector I can write with using some combination of these things.
Yes, what is the
Yes.
name for this vector? It's there's some special name, right?
I don't know the name. So if I have x comma y comma z, I will write x times e1 plus y times e2 plus z times e3. Okay. So which means that this e1, e2, e3 are enough to basically write everything as linear combinations.
Yes.
Right? Other vectors are linear combination of these vectors. And if you, in general, if you take a bunch of vectors and then take all linear combinations, that's called the span.
Wait, I didn't understand because what is the span? So what if the question asks what is the span of this vector? How would you answer that?
It's not a span of a vector, but in general, span of a collection of vectors is set of all linear combinations. Let me write it down.
Yeah, can you give me I wanted to actually understand what this word
Yes.
here.
So if I have say span of, let's say I have vector v1, v2, and v3.
Okay, that's the question.
Okay. So then this is the set. This is collection of all vectors, which will have c1 times v1 plus c2 times v2 plus c3 times v3.
What is C now? You've introduced
Where for all real values of C1,
because you can
choose anything you
multiply
want.
them by anything
Yes,
and
anything and then add,
any
and
scalar.
that's called a linear combination.
Got
And then you can
it.
create any linear combination and collect all of this together. That's called the span.
Got it. Okay. Got it. That makes sense.
Okay. So
Yeah.
this is basically anything like all the vectors I can create starting with v1, v2, v3.
Got it.
Because vectors I'm allowed to do only two things. So I can add the vectors and I can do scalar multiplication.
Yes.
So if I am given three vectors, this is all the combinations I can create out of those.
Makes sense.
So that's called the span.
Got it.
Okay. Geometrically, you should span off this way. So if I have a vector say pointing in one direction and another vector pointing in another direction, let's say both are on the horizontal plane, like flat on my surface.
Yeah.
Then by combining these two vectors, I can create the whole surface, whole flat surface.
Yes. Yes, that's
so that's the span of these two vectors.
Got it.
If I have another vector say going vertically up, these three vectors I can combine to create the whole 3D space.
Yes.
So then the span will be the 3D space.
Yes. Got it. Makes sense.
Okay. So
because there's some linear combination of those two that'll cover those spaces.
Everything.
That makes sense.
The whole of the space.
Got it. Why is the span important? What does that show?
Span is important because think of this way. So let's say I have, I'm trying to do a linear regression. Let's say I have two regressor height and weight.
Okay.
And I have a bunch of other regressors, but let's not worry about that.
Okay.
And then I'm trying to predict your blood pressure.
Okay.
Okay. So then if I have the height vector, think of height as a vector in abstract sense.
Okay.
And weight as a vector in some abstract sense.
Okay.
And then I'm trying all linear combinations of those does any of those look similar to the blood pressure?
Ah, okay.
If it does, that means height and weight can be like has a linear formula in terms of blood pressure.
Ah, okay. Got it. Got it.
Okay.
Okay.
So we are allowing any linear combinations and see which ones gets close.
To that. Yeah.
So the linear regression that you do actually has a geometric interpretation that way. It's the closest vector to the target within the span.
Closest vector to the target within the span. That makes sense.
Yes.
That makes sense. Yes, that makes sense.
So I look at all the span of all the vectors that I'm allowed to use in
Which
the
will be your
regression set,
regressors.
which
Yeah.
will be the linear regression because no linear
Got it.
combinations. And
Okay.
then I see whichever is the closest to the target.
Yeah. Okay.
Yes. And closest usually in geometry means you drop a perpendicular.
That I didn't understand.
So if you have a point, you have the horizontal plane, that is the span,
Okay.
and you have a point, say, slightly above that plane.
Oh, perpendicular meaning what is
So
that?
you drop a perpendicular from that point.
Yes. Okay.
So
Got it.
that is the point on the ground corresponding to the point which is floating. That ground point is the closest to the point, the aeroplane that is floating, let's say.
Got it.
So the nearest ground point.
Yes. On the because you're in another plane.
Yeah, you are on the plane.
Yes.
And you are like the aeroplane is above.
Got it.
So that's why like a span is basically anywhere you are trying to fit something. And then we have a concept which is linear independence. So linear independence is, we say that the collection is linearly independent if span doesn't contain the zero vector.
Linear independence.
So what we are trying to do here is that suppose some linear combination of these vectors is zero vector. So let's say 5 times v1 plus 7 times v2 plus some 11 times v3 is 0. Then I can take v3 on one side and write v3 in terms of v1 and v2.
Yes.
Which means that the original collection that I had v1, v2, v3, I don't actually need v3 because I can create v3 out of v1 and v2.
Ah. But then can't you just multiply them all by 0 to get the 0 vector?
Yes, other than, so I should add that caveat.
Oh, other than the zeros being.
All coefficients 0.
Okay, wait, I want to wrap my mind around the. So if you multiply them by some coefficients and you end up having a
Zero vector.
those
That means
are
I can take one of them to the other side and then write that one as a linear combination of the rest of the people.
Yes,
So
agree.
v3 is something, some combinations of v1 and v2. That means to create the span, I don't need v3. I could have done with v1 and v2 alone. Because any v3 is again a combination of v1 and v2.
Yes.
So that means there was basically something extra in my original starting set that I didn't need. So there was some dependency.
Can we pause right here? What does that
Yeah.
mean in like 6th grade algebra? Because I'm trying to relate it also to like, so I guess that means that your one like in the third, if your simultaneous equations are there, then
Yes.
that would mean that you
That means basically that the third equation follows from, say, by adding the first two equations.
Makes sense.
Then you are not getting any extra information from the third equation.
Yes. Okay. Yes, that makes sense. Complete sense. So that's linear dependence then.
Yeah, that's the linear dependence.
Okay.
And if there is no linear dependence, then we call it linear independence.
And why is linear independence important?
Because when you are trying to do linear combination stuff, we don't want to add a bunch of extra stuff which is not adding any value.
Not adding any
So
value.
let's say you're doing linear regression. If I use 5 or if I use 50, I'm getting the exact same fit. So I should use 5 rather than using 50.
Got it. Got it.
I should not add any extra variable. So if I'm adding an extra regressor, it should justify its merit.
Usage of that. Okay. Amazing.
Okay. There is another reason, which is if you have linear dependence, then some math somewhere else will fail
Yeah.
later on when you are doing some calculations.
And we can solve for the linear independence by doing the elementary row operations, reduced echelon form, and solve.
Yes, yes, yes.
And then if
So
you
those
put
are
it in-
those are the computational ways of finding out linear dependence or independence.
Okay, that I know how to do. Okay, so we're good on that one.
I'm not going through the algorithms and stuff. I'll only just cover the maths part of it for now.
Okay. Yeah, because I think the algorithms, I think I can get.
Yeah, algorithms you can figure out later. Okay. Now, if you have, let's say, suppose some set S is a linear in-depth set, and its span is, let's say, V. Um, then we say that S is the basis for V.
Oh, I need to. These are all words that I haven't heard.
Yeah. We are introducing around 100 new words today. So this
Base.
should
I
go
forgot.
through. So basis is a keyword.
Suppose
I'll just highlight it.
X is a linear.
So you have a linear independent set. So this is just saying that S has nothing extra that you don't need.
Yep.
And then we calculate the span by doing all linear combinations, and we get something like V.
Yes.
Okay. So this V will be a vector space, meaning it is a collection of vectors which is closed under addition and stuff.
Yes.
Okay.
Yes.
So this vector space V, we say that the S is basis for it, meaning S is enough to create everything in V.
You lost me on that last sentence. If
So the set S is enough to create all the vectors in V.
set S is enough to create all of the why is the S different than your span?
The span is all the linear combinations. So let's say the set S is V1, V2, V3, and the span is all C1, V1 plus C2, V2 plus C3, V3. So then that span is the vector space V, but the basis is just 3 vectors. So those 3 vectors are enough to create all these linear combinations, which is infinite collection, right?
Okay. So then the basis is like a small down version of the.
Yes, small down version, which is enough to create the whole thing if you need to.
Which is enough to create the whole thing out of there. Okay.
And this basis is usually like 2, 3 things, or 5 things, or 10 things, whereas the full collection is infinite.
Is there like in this book that you sent here, is there like an example problem? You don't have to go immediately into it because I know it might take some time to make up the problem, but is there like find the basis of this and then it walks?
Yeah, there are lots of problems like that. Just scroll down to wherever the basis is introduced. You'll give a lot of examples.
Got it. Okay. I'll go through that then and see. Okay.
So we have understood what the vector space is and what is the basis for a vector space. I will give you some simple example. Let's say V1 is 1, 0, 0, and V2 is 0, 1, 0. Okay. Now, if you take all the linear combinations of these two things, you will always have the third coordinate 0 because third coordinates both are 0. So then V will be all, let's say C1, C2, 0. This collection. This makes sense? If I do C1, V1 plus C2, V2 plus C1, V1 plus C2, V2, that's it.
Okay. And then your S.
So my S is just V1 and V2. S is V1, V2.
Then what is C1 V1 comma C2 V2? What do we call that?
No, C1 V1 is a vector plus C2 V2.
C2 V2.
So let me write it down. So C1 V1 is C1, 0, 0, and C2 V2.
Yes. Okay.
0,
C2, 0.
0. And then I add these two up. So C1 V1 plus C2 V2 is C1, C2, C2. Make sense?
Yes. Is there a name for the C1 V1 plus C2? What I guess I'm asking.
The linear combination.
That's just linear combination. Okay.
And we form all such linear combinations, we get this vector space V.
Amazing.
Where basically now C1 and C2 can be arbitrary real numbers.
Amazing.
Because you can put any C1 and C2 here, and you can create it like this. Like by C1 V1 plus C2 V2.
Makes sense.
Okay. So now this V is a vector space. This is not like all vectors. This is just all points where the Z coordinate is 0.
Yes.
Which is like the XY plane.
Yes.
Okay. And this set S is a span for that.
Yes.
Just two vectors. Okay.
Yes.
Of which say V1 is basically the x-axis kind of thing.
Yep.
And V2 is the y-axis.
Then we can take linear combinations of that. Yes.
Yes. So basically XY plane is spanned by x-axis and y-axis. That's all we are saying. Make sense?
Yes, sir.
Similarly, you can do a YZ plane or XZ plane or any like or non-orthogonal kind of plane, any slanted kind of thing and all that.
Yes.
If you take linear combination, you get if of any two vectors, you will get a plane. Okay? Now this vector space, the XY plane, this is not the full vector space, but it's like a subset vector space, so we call it a subset, subspace. So subset of vector space, which is a space on its own, basically. By space on its own, I mean that you can do linear combinations within this subspace and it will lie there. So it's like a fully spanned kind of thing. This is good.
What is the difference between okay, so the difference between subspace and vector space is that subspace is a subset. But
Yes.
how do you create that subset?
I created by doing all linear combinations.
But all linear combinations should be the entire vector space then, right?
No, because I took only two vectors. I didn't take the V3.
Oh, right.
If I had done V1, V2, V3, then I would have gotten everything. Because I took only two of them, I got something smaller. Like not everything is spanned here
Got
by
it.
these two guys.
Okay. Okay.
Okay.
Yes.
So this is a subspace, and then we have already covered the basis of vector space.
Yes.
Okay. Now, if you have a subspace, then it has a basis because we know what vectors it was spanned by. So V1 and V2. So dimension is just number of elements in the basis. So how many vectors do you need to span this? So for example, this subspace was spanned by two vectors.
So non-zero
Yeah.
elements then pretty much.
Yes. Yes. So you need just two non-zero vectors to span the whole thing. So that means it's dimension 2. Whereas the whole thing, I needed 3 vectors, so it was dimension 3. So we'll say that this is a 2-dimensional subspace of a 3-dimensional vector space.
Makes sense. That makes sense.
Okay.
Yes.
So this is how people usually talk about that I have taken a 2-dimensional subspace of a 3-dimensional vector space.
That tells you a lot.
Yeah.
Just by that.
Yeah. Now dimensions can be very large. It can be 100,000.
Yes.
It can be infinity also sometimes.
Oh.
So for example, I'll give an example that we already discussed. So you remember the polynomials?
Yes.
So what will be the dimension of the polynomial vector space? There's no limit because you can take polynomial of any high degree.
Oh, because the constant itself can be whatever you want it to be.
No, so I can take x power n, where n is any high number.
But we're not. Oh, okay.
So if I have to put x power n, that will go to the nth coordinate.
Yes, but what about the coefficient? It's like what that doesn't matter though. No, that
doesn't matter.
You're talking about the dimensions.
Yeah.
Okay. Yes.
So every 1x, x square, all these are like individual coordinates for me.
Yes.
Individual basis vectors.
Yes.
So dimension is total dimension is infinite.
Yes.
But if I restrict, say I will only take polynomials up to degree 3, then that will be a 3-4-dimensional space.
Yes.
It will actually be 4-dimensional because the constant term is 1 and then 1 x square x cube.
0, 0, yeah.
Total 4 dimensions. Okay.
Okay.
So we can create very easily infinite dimensional vector spaces like this. And there are a lot of others also.
Got it.
Okay. So we can talk about dimensions and all. Dimension is like a really huge thing, an important thing in machine learning because basically we're trying to learn.
Curse, isn't
Yeah,
there something curse of dimensionality or something?
yeah. Curse of dimensionality is one of the like biggest problems in machine learning. That the more and more higher dimension you try to work on, any of the standard methods don't work as well as you like. Like whatever works well in low dimension doesn't work well in high dimension.
Got it. But then
So you
wouldn't
need more and more data points to fit to the your regression or whatever you are doing.
wouldn't it be more and more features or regressors as opposed to more and more data points?
Uh, in terms of regression, so features, number of features decides your dimension.
Yeah, exactly. Exactly.
Yeah,
Yeah.
number of features decides your dimension. And say I have 100 features, I can fit with maybe 5,000 points. But if I have million features, then I need billions of points to fit that. And
Yes.
even then, things can go wrong.
Yes. Yes.
So that's where the curse of dimensionality is a very important topic in machine learning. So
Cool.
any of the algorithms, any of the techniques you learn, you try to understand how it is affected by dimensionality, whether it is good enough for any dimensions. There are some techniques which are good enough for all any, like it doesn't care about the number of dimensions. But so that's like an added advantage of that method.
Got it.
Good. So next we'll do the multiplication of vectors, which is dot product. So
Oh,
if I
just
have two
need
vectors,
because we can do scalar multiplication and vector addition, but now
yes, we don't have multiplying two vectors yet.
we can't. Yeah, so we have to do. I remember this dot. I don't remember how to do the dot product.
Yeah,
Remember it was
so we'll
being a
do
little
something like
hard,
this.
right?
So let's say I have a vector x, which has coordinates x1, x2, up to xn. And I have another vector y, which should be y1, y2, yn. So then I will denote x dot y. This is my notation for now. So it will be just x1. So whatever you think you should be doing coordinate wise, x1, y1. And then you add up all these things up to xn value.
Wait, I
That's
thought
it.
you can't do that.
We can do because x1, y1, I'm not creating a vector. I'm creating a scalar by adding all these things. So dot product is a scalar. It's
Oh,
not
you're
another vector.
adding all of them together.
Yes.
Oh, it's not individual elements
No,
then.
it's not into. I'm not trying to create another vector. That so if you try to create another vector, it runs into a lot of problems. Some of those which can be resolved in some ways and all, but that's complicated. But if you add up all them, then it's just one number.
So
Doesn't matter what you do.
multiply two vectors together. What is that in real life? Like what? I don't can. Okay. Okay.
Yeah, so this has two different meanings. One is how do you think about length of a vector? And second is how do you think of angle between vectors? Okay.
Okay.
So we'll define these two things. So length of a vector x is square root x dot x. And I will explain what this means. Let me just with x and y.
That's it
Let's
seems
say
like
angle is
doing
theta.
some kind of like either distance formula here or Pythagorean theorem.
Yes, yes. We are trying to use the distance formula.
Angle between them. That means magnitude, I guess.
No, the angle between two vectors.
Or no, the absolute value sign.
Yeah, that is absolute value. So that is my notation for length.
Length. Isn't that
Okay.
called magnitude? No, that's
Yeah,
not.
that's called magnitude. So the physics thing that people talk about, vectors have magnitude and direction. So this is where it comes from mathematically. So the
Vectors have
magnitude is given by square
yes,
root of x
yes,
dot x. Yeah.
yes. Okay, that's coming back. Yeah.
Yes.
Are you
So
good
now
in
if you
physics?
do x dot, yeah,
Are you good in physics also?
a little bit. I don't remember a lot of stuff. Yes. So this x dot x, if you write down the formula, you will get square root of summation of the x squares. So you'll get x1 square plus dot dot dot, all the sum of squares kind of thing. This is the usual Pythagorean formula for length, right? The hypotenuse square is base square and
Yes.
altitude square and so on. Now, if you have multiple dimensions